So I'll just, for those of you who didn't attend on Tuesday, start with a very brief introduction about my academic background. So I did my undergraduate degree in France. I did a double major in maths and physics. And then last year I came to the UK to do my master's in mathematical and theoretical physics in Oxford. And I specialized in theoretical particle physics. And this year is my first year of DPhil or a PhD, so those mean the same thing, in the mathematical physics group in the Maths Institute in Oxford. And also, before starting this session, I do want to say that, as in the case in representation theory, quantum mechanics is quite an advanced topic. I first saw it, so I had a very brief introduction in high school, but otherwise I took my first course in quantum mechanics in my at university level in my second year of undergrad. So I really hope today to give you an introduction to the main ideas in quantum mechanics. But again, if some concepts seem a bit unclear, even by the end, you shouldn't worry too much. I really hope that I will give you a good introduction. But if you have any questions, of course, I'm very happy to take them throughout the session or at the end of the session. So then let me start by introducing you to quantum mechanics from a slightly historical perspective. So first of all, what is quantum mechanics? Quantum mechanics is a fundamental theory which describes the behavior of matter and light at and below the scale of atoms. So when I say the scale of atoms, we're talking approximately 10 to the exponent minus 10 meters. So most of you are probably, at least to some extent, familiar with classical mechanics and Newton's laws, the first, second, and third Newton laws. So in classical mechanics, you study objects and then you know that you have forces acting on that object, and then you can compute the trajectory of your object. And you probably all know Newton's law of gravitation, which gives you the magnitude of the gravitational interaction between two bodies. And this is all a very good description of gravitational interactions in our universe when we are at very big scale. So, for example, you can use Newton's law of gravitation to compute the magnitude of the gravitational interaction between the sun and the Earth or any other planet. So, at the at these scales, at very big scales, so the scale of planets and stars, classical mechanics and Newton's laws are a good description of the interactions in our universe. However, as we go to smaller and smaller scales, and when we arrive at the scale of atoms, this is no longer true. So so classical mechanics no longer captures, it doesn't explain phenomena and processes that we see that happen at the scale of atoms. So it doesn't mean that it's no longer, that the laws are no longer true. It just means that because gravitation is no longer the dominant force at the scale of atoms, classical mechanics no longer um, provides a good description of the processes and phenomena that happen at the scale of atoms. And that is precisely what quantum mechanics does. It provides the description of the behavior of matter and light at and below the scale of atoms. Quantum mechanics was developed in the early 20th century. So in the early 20th century, we had classical mechanics, which was developed before the 1900s, and then we had the emergence of of quantum mechanics. And so let me then start by very quickly reviewing the description of matter and light in classical mechanics. So we have matter, for example, electrons, protons, neutrons, or quarks, and Thomson said that electrons are particles. And when it comes to light, in the 1670s, Newton devised a corpuscular theory of light. So he devised a theory of light in which light is composed of particles or corpuscles. So that's why we call it a corpuscular theory of light. Then eventually, this was replaced by an undulatory theory. So you might all be familiar with Maxwell and electromagnetism, or at least have heard of it. So what Maxwell said is that light is an electromagnetic wave. So this is an undulatory theory. So that's what happens in classical mechanics. Light, there was Newton's corpuscular theory, which eventually was replaced by Maxwell's undulatory theory of light. And now, the birth of quantum mechanics can really be associated to Planck and his study of blackbody radiation. So thermal radiation is the radiation emitted by any body, and here when I say body, I mean any object, any system, because of its internal energy. And by radiation, what I mean is it is energy emitted in the form of an electromagnetic wave. And so if you have any body which has some internal energy, it will emit thermal radiation. And if you heat that body, then you provide more and more energy to that body, and then you will see a shift in the color that is emitted by the body. And some bodies, we say, are perfect emitters. So they, in some sense, emit in a perfect way. So you can see an analogy here if you've done chemistry in already. You might be familiar with ideal gases, which are these gases which are kind of a perfect model. They are this ideal type of gas. And here it's you can see an analogy. So a perfect emitter is a body that emits thermal radiation in a kind of perfect or ideal way. And these perfect emitters are also what we call perfect absorbers, meaning that they perfectly absorb all the radiation that is emitted on them. And so if your perfect emitter or your perfect absorber is cold, then it is perfectly black, which is why we call it then a black body. So a black body is a perfect emitter slash perfect absorber of thermal radiation. And this thermal radiation emitted by a black body, so black body radiation, was studied quite extensively, and several attempts were made at devising a theory, a law that would explain the experimental results. So one of these laws is the Rayleigh-Jeans law, which is a classical one, and that's the one in red, which you can see in the graph. So the graph that I'm showing you here is a graph of radiance as a function of frequency. So essentially, it gives you the amount of thermal radiation emitted as a function of the frequency that is emitted. And the Rayleigh-Jeans law very well, so it fits the experimental results very well for short frequencies, but not for high frequencies. So if you take so if you go to the right on your x-axis, so you take your frequency to infinity, then you see that the radiance becomes infinite, which is really inconsistent with reality, with what you would expect from experiments. And this is what we call the ultraviolet catastrophe. Now, another law which attempted to explain blackbody radiation is Wien's law, which is the one that you can see in blue. This one, in contrast to the Rayleigh-Jeans law, it fits experimental results very well for high frequencies, but not for short frequencies. And then finally, Planck, and so for those of you who haven't heard the name, so this Planck is a person, devised a law called Planck's law, which is the one that you see in green. And this law fits experimental results very well for any frequency. And in order to devise that law, Planck had to postulate that energy is not emitted in a continuous way, but instead it is quantized. So meaning that essentially your energy is emitted in small packets, so small quanta of energy, rather than just some kind of continuous wave of energy. And he said that each of these quanta of energy have energy E is equal to h times F. So here, h is a constant of proportionality, which we call Planck's constant, and it's equal to 6.63 times 10 minus 34 joules second. And F is the frequency of the associated harmonic oscillators. So without going into the details, you can just see thermal radiation as corresponding to, so the radiation is emitted because of the oscillation of harmonic oscillators, and these harmonic oscillators have a frequency f, which is the one which appears in the expression for the quantum of energy. So the quantum of energy is proportional to the frequency f of the harmonic oscillators, and the constant of proportionality is Planck's constant. And this was really a completely new concept, this idea that energy would be quantized. Planck said that he postulated this quantization of energy in an act of despair. And now moving on, another very important effect in the birth of quantum mechanics is the photoelectric effect, which was given an interpretation by Einstein. So the photoelectric effect is an effect that you would obtain if you emit light on a metal surface. If the incident light satisfies some conditions, then some electrons will be emitted from the metal surface. And these electrons will be emitted with kinetic energy, which is the energy that they have because they are moving. And the kinetic energy of an electron which is emitted is given by the equation E is equal to h times F minus W0. So here E is, as I said, the kinetic energy of an electron that is emitted, and W0 is a number which depends on the metal that you are considering, and which is called the work function of the metal. So essentially you can see this this work function of the metal as an energy that is keeping your electrons to the surface. So if the energy of the incident light is smaller than the work function of the metal, then there is more energy keeping the electrons to the metal surface, and so no electrons will be emitted from the surface. On the other hand, if you send enough energy, so if the light that you send onto your metal surface has enough energy, then you will manage to emit electrons because the energy keeping the electrons to the surface is surpassed. You sent more energy than the amount of energy keeping the electrons to the surface. And then finally, for the third term in the equation, you will recognize, hopefully, from the previous slide, the quantum of energy hf. And here, h is again Planck's constant, and f is the frequency. And what Einstein said, so here I'm not going to specify again what the frequency is yet, but what Einstein said is that rather than any quantum of energy, the energy E is equal to h times F is the quantum of energy corresponding to a particle which he called photon. So here, F is the frequency of a particle in your light that Einstein called a photon. And that is the really revolutionary statement that Einstein made, that light sometimes behaves as a set of particles, which he called photons. And so, in quantum mechanics, electrons are both particles and waves. And for the description of light, so light is both corpuscular and undulatory. And what was observed is that electrons and light have similar properties. So you have several applications of quantum mechanics. One of them, which you probably use quite often, is the GPS. So it does need to use the principles of quantum mechanics to ensure the accuracy of the position that is computing. Nuclear energy, nuclear magnetic resonance, or lasers are other applications. And then you also have developing applications like, I'm sure you've all heard of quantum computers, which are these computers which use the principles of quantum mechanics. You have quantum cryptography or high temperature superconductors, brain imaging, and so on. And before introducing you to the postulates of quantum mechanics, I'm going to introduce you to this double slit experiment, which was initially at least a thought experiment. And this, I think, will give you a good intuition of the main ideas in quantum mechanics, which then will make it easier for me to introduce the postulates of quantum mechanics. So, as I was saying, the double slit experiment was at least initially what we call a thought experiment. So, this comes from the German Gedanken experiment, which literally means thought experiment. And so what we mean by a thought experiment is an experiment that you don't perform physically in a lab, but you could say somehow that you perform the experiment in your mind. So you kind of think the experiment rather than perform the experiment. So the double slit experiment, you have a gun which fires some object. So you can choose the object that your gun is firing. A bit further away, you have a wall with two slits, which we label 1 and 2. And even further away, you have a backstop, which is just a wall that prevents the further progression of the objects fired by your gun. And on this backstop, you have a movable detector, which can detect the position of the objects that arrive on the backstop. And so more precisely, it measures the position x, and we take x is equal to 0 to be in between the two slits, and then x increases upwards. And what you want to do is to measure the probability of arrival of your objects at position x. So now it's important to understand that. So in classical mechanics, as I said to you at the beginning, you have some object you can apply. If you know the forces that are applied on that object, you can know very precisely where your object will be at some other time. You can determine its position precisely. Here, because your gun fires many objects at the same time, you can only consider measuring the probability that your objects arrive at a given position x. You can't, for example, consider, oh, I have this specific electron and I do Newton's laws, and then I know that my electron will be here. No, you can only compute the probability that your electrons will arrive at some position x. And to be even more precise than that, what we measure is the probability density function pi of going through slit I. So a probability density function is just a function that depends on some argument, and when you evaluate it at the argument, then you get a probability. So essentially it's a function, and when you apply that function, then you get a probability. So here we have two slits, and we're interested in computing P1, the probability of going through slit 1, and to be more precise, to be more accurate, the probability density function of going through slit 1, P2, which is the probability density function of going through slit 2, and then we also have P12, which is the probability density function of going either through slit 1 or 2 or both. And so to really hopefully make you understand what a probability density function is. So Pi is a function. It is a function which depends on the position x. So Pi is the probability density function of going through slit I, and it depends on the position x. Why? Because it might be the result that you get, so the probability of having gone through slit I might be different depending on if you consider x is equal to 0, or if you consider x is equal to plus infinity or minus infinity. So Pi is a function. It's not a probability per se, it is a function that depends on x. And then when you compute Pi of x, then this is your probability of having gone through slit I and arrived at position x. So really you have Pi, which is a function, the probability density function of going through slit I, and Pi of x, when you evaluate it at x, you get the probability of arriving at x and having gone through slit I. And your double slit experiment, you start by performing it with bullets. So your gun is firing bullets. Then what you observe is addition of probabilities, namely P12 of x is equal to P1 of x plus P2 of x. So let me explain why this result is quite intuitive. First, I should also mention that we are considering the bullets to be indestructible, meaning that they can't break into pieces. So, I think quite intuitively, since your bullets can't break into pieces, so if they arrive at position X, either they went through slit 1 or they went through slit 2, but they couldn't possibly go both through slit 1 and through slit 2. And that is why it follows that we get addition of probabilities. So let me discuss the general law of addition of probabilities. So the law of addition of probabilities is that if you have two events A and B, then the probability of the union, A union B, so A union B means either A happens or B happens or both, the probability of the union, so P of A union B, is equal to P of A plus P of B minus P of A intersection B. So it is the probability P of A that A happens plus the probability P of B that B happens minus the probability of the intersection. And the intersection A intersection B is just when both A and B happens. So P of A intersection B is the probability that both A and B happens. If you have disjoint events, meaning events that can't happen simultaneously, then A intersection B is equal to the empty set. So you have nothing, there is no intersection between your two sets. And then, of course, the probability of the intersection will be 0. And that is precisely what we observe here. Here we see that P12 of x, the probability of arriving at x, that your bullet arrived at x, and that they went through slit 1 or slit 2 or both, is equal to P1 of x plus P2 of x. So it's the sum of the individual probabilities, because the probability of the intersection, namely that they went through both slit 1 and slit 2, is 0. And so that is what you obtain, addition of probabilities, if you consider bullets which can't go through both slits at the same time. Now, if you perform your experiment with waves, so essentially you imagine that your gun is now pushing a wave towards your wall with the two slits, then what you observe is interference. So you don't observe addition of probabilities, but interference. So P12 of x is different from P1 of x plus P2 of x, and this means that the intersection, namely that the wave went through both slits at the same time, is not 0. And I think this, so if you try to visualize this, it is indeed not impossible that your wave goes through both slits at the same time. What you do observe if you perform the double slit experiment with electrons is, as some of you quite correctly pointed out, interference, which I think, at least for me, initially seems quite counterintuitive, because at least a few years ago, I saw electrons as these small particles, and then surely the electron wouldn't be able to go through both slits at the same time. But then what the double slit experiment shows is that we get interference, so that means that the electron is indeed able to go through both slits at the same time. So essentially, it behaves like a wave. Now, that's if we perform the double slit experiment with electrons, but as is. If we now really try to detect through which slit an individual electron went, so what we can do is to reduce the rate at which the gun is firing electrons to essentially try and make the gun fire electrons one by one. And we put light at the slit to identify through which slit the electrons went, then what we observe is that the probabilities add. So we don't have any interference anymore. So now the probabilities add, meaning that your electron did indeed only go either through slit 1 or through slit 2, but not through both at the same time. So what we understand here is that quantum interference, so the interference of the probability density functions, is destroyed upon observation. So when we try to detect the slit through which electrons went, then quantum interference is destroyed and the probabilities add. So really the key conclusion about the double slit experiment is that electrons behave both like waves and particles. And that's what we call wave-particle duality. So electrons behave like matter waves, like waves of matter. And because of that, so electrons have quantities associated to them because they are particles. For example, they have an energy and a momentum because they are particles. So these are quantities associated with particles. But because they are also waves, they have wave characteristics associated to them. So we can talk about the wave number k or the angular frequency omega of an electron, because the electron is also a matter wave. More precisely, it is a kind of electron wave, you could say. And de Broglie stated the relation between momentum and wave number and energy and angular frequency. So he said that the relation between the momentum p and wave number k of an electron is p equals h bar k. And here h bar is just what we call the reduced Planck constant, which is h divided by 2 pi. And the relation between the energy E of your electron and its angular frequency omega is E is equal to h bar omega. And so really important to which what also follows from the double slit experiment, so really important to understand is that when it comes to the quantum mechanical description of subatomic particles, on the one hand, it is a probabilistic description, because remember, as I told you, you can only consider measuring the probability for your objects to arrive at, or for your electrons to arrive at some position x. So because of you are considering this set of particles, you need a probabilistic description, but the quantum mechanical description is also a wave description, since your electrons are both particles and waves. And a very important idea of, or I mean, the concept of quantum mechanics is it's really a theory of measurement. So you measure observables, and here by observable, I mean a physical quantity that you can measure, for example, energy, momentum, or position. So in quantum mechanics, you measure observables and you get different outcomes. And what you do is that to each outcome, you associate a probability. So that is really a key idea of quantum mechanics. So it is a theory of measurement. You measure observables, and to the outcomes of your measurements, you associate probabilities. Now, a particle has what we call a quantum state. The state of a particle, the quantum state of a particle, is just the set of quantum information which characterize that particle. And quantum mechanics describes the state of a particle through the use of a wave function. So, and to be more precise, the mathematical object that describes a particle state in quantum mechanics is what we call a wave function. And now finally, I'm introducing you to the postulates of quantum mechanics. So first postulate, the quantum state of a particle in quantum mechanics, so the set of quantum information that characterize the quantum state of your particle is described by a complex wave function psi of xyzt. So let me unpack what we mean by a complex wave function. So first of all, it is a function. It is a function like any function you are familiar with. It is a function that depends on x, y, and z, the three components of the position of your particle, and it also depends on time. Wave function, we call this function specifically a wave function, and complex because it can take complex values. And perhaps I should just give you an example actually of what the quantum state of a particle is. So some of you might have done chemistry, in which case you might be familiar with the description of electrons in your atoms. An electron in your atom is entirely described by four quantum numbers. So these quantum numbers entirely specify the quantum state of your electron. So you have the principal quantum number n, then the secondary or azimuthal quantum number L, and then you have the quantum number m, which characterizes the quantum box in which your electron sits, and then finally you also have the quantum number spin, so spin up or spin down. And so these four quantum numbers entirely characterize your electron, the state of your electron in your atom. So these quantum numbers entirely specify the quantum state of your electron. So now back to the wave function, which describes the quantum state of your particle. So the wave function doesn't have a physical interpretation, meaning that you can't see it as some physical quantity, like, oh, the wave function is the energy of my electron. No, the wave function doesn't have a physical interpretation, so it doesn't correspond to an observable physical quantity. However, the squared modulus of the wave function does have a physical interpretation. It's the probability density function to find the particle at a given position at a given time. So P is your probability density function, and when you evaluate it at x, y, z, and t, meaning that you consider p of x, y, z, t, then this is the probability of finding your particle at position x, y, z at time t. And now this probability is equal to the squared modulus of your complex wave function psi of x, y, z, t. And because the probability that your particle is somewhere in space is 1, the integral on the slide here evaluates to 1. So let me try and make you visualize this. So if you take a box and you put a particle in your box, and then you're wondering what is the probability that the particle is in the box? Well, the probability is 1 because your particle is definitely in the box. Now, if you were to only consider a subregion of your box, then the probability to find that particle in that subregion might not necessarily be 1, since there is a probability that it is in another subregion of your box. But if you consider the whole box, then definitely the particle is in it, and so the probability to find your particle in the box is 1. And that is exactly equivalent to the integral on this slide. So if you take your probability to find your particle at position xyz at time t, this is p of xyzt, and you integrate this with respect to x, y, and z, and each time, so x goes from minus infinity to plus infinity, y goes from minus infinity to plus infinity, and z goes from minus infinity to plus infinity. Then what you're doing is that you're integrating your probability over the entire space. So you're considering your probability to find your particle at x, y, z at time t for any x, for any y, and for any z. So you're really integrating over space. So this amounts to computing the probability of finding your particle anywhere in space. And that's why this is equal to 1. And then finally, really the absolute key postulate of quantum mechanics is the superposition principle. So what the superposition principle says is that if psi1 and psi2, and perhaps I should mention, if you haven't come across this letter before, psi is just so it's just the Greek letter for the wave function. That's what it's called, psi. So if psi1 and psi2 are wave functions which describe two possible quantum states of your particle, and if you now multiply psi1 by any complex number c1, and you multiply psi2 by any complex number c2, and then you add the two together, then what you obtain, c1 psi1 plus c2 psi2, is also a possible quantum state for your particle. So really what the superposition principle says is that if you have two wave functions, so corresponding to two possible quantum states of your particle, and you consider a linear combination. So a linear combination just means that you multiply each, so you multiply psi1 and psi2 by some coefficient and you add the two together, then this also describes a possible quantum state for your particle. And really, I can't emphasize enough that the superposition principle is really the key postulate of quantum mechanics. Now, I'm going to just introduce you to observables and operators in quantum mechanics, which are how we compute things mathematically in quantum mechanics. So remember, the quantum state of your particle is described by a complex wave function psi. Now, there are also some things, some quantities associated to your particle, or I should say your particle has some quantities like energy, momentum, and position that can be computed. So they are physical quantities that you can measure. And that is precisely the definition of a physical observable. A physical observable is a physical quantity that you can measure. And now the quantum state of your particle is described by a complex wave function psi, but you could also associate a vector which would describe the quantum state of your particle. And this vector, which is associated to the wave function describing the state of the particle, so which is associated to the state of your particle, we call it ket psi. And this ket notation was introduced by Dirac. So this is called the Dirac-Ket notation. So the Dirac-Ket notation is the notation included here on the slide. And this ket psi is the vector that corresponds to the state of your particle if psi is the complex wave function describing the state of your particle. And because ket psi is a vector, it belongs to what we call a vector space, which is just a space whose underlying set, so the elements in your vector space are vectors. Now, if you're in a lab and you have a particle which is in a given quantum state, and usually we'll talk about a state rather than a particle within a given state. So if you have some quantum state, you can act on that quantum state and transform it into another one. Or in other words, so if you have a particle which is in a given state, you can do some things in order to change the quantum state of your particle. So then what you do is that you modify the wave function associated to, so it doesn't evaluate to the same thing anymore. And mathematically, the way that you implement your transformation of the quantum state is that you apply a function which we call a linear operator on the associated ket. So you have some particle whose quantum state is described by the wave function psi, and there is an associated vector ket psi, which is an element of a vector space V. And now, in order to transform the state of your particle, you act on ket psi with the operator O hat. So hat, putting a small hat above that's the notation for operators. So you act on ket psi with your operator O hat, and then what you get is O hat ket psi, which is a different vector. It's another vector in your vector space. So that is what a linear operator is. It is a function that acts on your ket psi in the vector space and gives you back O hat ket psi, which is ket psi transformed by O hat, which is again in your vector space. So it transforms your initial state into your final state. And in quantum mechanics, physical observables, such as, remember, energy, position, momentum, are associated with a specific type of linear operators, which we call Hermitian linear operators, or just Hermitian operators. For example, then, to energy, which is a physical observable, you can associate a Hermitian operator, which we call the Hamiltonian, and which we denote by H hat. So we also call it, the Hamiltonian or the energy operator. And then similarly to momentum, you can associate a momentum operator. Position has an associated position operator, and so on. And now remember that in quantum mechanics, you perform measurements, you measure physical observables, and to the outcome of these measurements, you associate probability. So you want to compute the value and actually the average value of observables when your particle is in a given state. And in quantum mechanics, the average value of a physical observable in a given state is equal to the expectation value of the associated Hermitian operator in that state. And here really I want to emphasize that we say in a given state. So the quantum state of your particle is described by psi, and the average value of your observable could change depending on which quantum state your particle is in. So depending on psi, you could get different average values for an observable. So that's why we always talk about in a given state. So you compute the average value of an observable knowing that your particle is in a given quantum state. And that is the equality. That is what it says, that the average value of an observable in a given state is the expectation value of the associated Hermitian operator in that state. So you compute, if you want to compute the average of some physical observable O, then that is O bar. And truly, sometimes you will also see a small sub psi to really emphasize that we are considering the average value of O in the state psi. This is equal to the right-hand side, and the right-hand side is just the notation for the expectation value of the Hermitian operator O hat associated to O. So the way you compute this, you can see this as a multiplication of vectors and matrices. So ket psi, it is a vector, it is a column vector, and then when you see ket psi but on the left-hand side, that is what we call a bra. So it's bra psi. And then your Hermitian operator O hat can be represented by a matrix. So then when you're computing the expectation value, what you're doing essentially is multiplying your bra psi, which is a line vector, by the matrix corresponding to O hat, and this you multiply by the column vector ket psi. And so just to give you an example, if you wanted to compute the average energy of a particle in the state psi, then you have E bar, so the average of E in the state psi is the expectation value of the Hamiltonian operator in the state psi. And I'm going to end my session by introducing you to the Schrödinger equation, which I want to call the master equation in quantum mechanics. It really is the key equation in quantum mechanics. And this equation governs the dynamics of the wave function of a particle. So the dynamics, this is just essentially the evolution in time. So the Schrödinger equation governs how the wave function associated to a particle evolves in time. And so remember that the wave function associated to a particle, it is what describes the quantum state of your particle. So essentially what the Schrödinger equation governs is the evolution of the quantum state of your particle in time. And so I'm sure perhaps it looks quite fancy with the symbols partial derivative and psi and h hat, but I'm going to unpack this equation for you. Really, it's not, at least conceptually, that complicated. So the Schrödinger equation, on the left-hand side, you have I, which is just the complex number I, multiplied by h bar, the reduced Planck constant, and this is multiplied by the partial derivative of psi with respect to time. So partial derivative is just the type of derivative that you need to use when you are considering a function that depends on several variables. So remember that your wave function psi depends on 4 variables, x, y, z, and t. And so if you are considering the derivative of psi with respect to a specific variable, for example, t, then you need to use a partial derivative. So what the Schrödinger equation says is that IH bar multiplied by the partial derivative of psi with respect to time is equal to h hat times psi. So your Hamiltonian operator h hat, the energy operator, acting on the wave function psi. And so essentially what this means is that the Hamiltonian really dictates the evolution of your wave function in time, since if we can integrate this equation, then we get, so we integrate it with respect to time, then we can get psi of x, y, z, t for any time t. And when you integrate this equation, the result that you will get, the solution psi that you will get, depends on h hat acting on psi. So that's why we can say that the Hamiltonian operator really dictates the dynamics of the wave function of your particle. And now I'm just going to tell you how we find this Hamiltonian operator. So in classical mechanics, the mechanical energy of your particle is the sum of the kinetic energy and the potential energy of the particle. And I'm not going to consider systems such as springs, which have this additional energy due to the spring nature. And if you consider a particle, then its kinetic energy, so the energy that it has because it's moving, is 1/2 of mv square. And because there is a relation between the linear momentum p and the speed v, we can re-express this in terms of the linear momentum. So the linear momentum you might have come across already is p is equal to m times v. So it's the product of the mass of your particle and the speed of your particle. So we can rewrite that the kinetic energy of your particle, 1/2 of mv square, is equal to p square divided by 2m. And now the potential energy of your particle is just v of x, the potential in which your particle is. So the mechanical energy of your particle will just be p square over 2m plus v of x. And then the way you obtain your Hamiltonian operator is by essentially to each physical observable in the expression of your energy, you associate the associated operator. So essentially, we could say you transform your physical observables into the associated operators. And so that is how you get that your Hamiltonian operator H hat is equal to P hat square divided by 2m plus V hat. So now P hat, we are considering the Hermitian operator P hat associated to momentum. So we are considering the momentum operator P hat. And by V hat here, truly what we mean is V of X hat, because the two physical observables in the expression of your energy are the momentum, the linear momentum P, and the position X. And so you transform P into P hat and X into X hat. And so we write the shorthand notation V hat, and that's how you get your Hamiltonian operator. It's P hat square over 2m plus V hat. And now your momentum operator has a specific expression which allows us to rewrite the Hamiltonian operator as minus h bar squared divided by 2m Laplacian. And so Laplacian is just an operator that essentially is computing second derivatives plus v hat. So that's how you find the expression of your Hamiltonian operator. Your Hamiltonian operator is h hat is equal to minus h bar squared divided by 2m Laplacian plus v hat in the case that you are considering a particle in a potential. And so just to end on an example of the Schrödinger equation, if we consider a free particle, meaning a particle that does not, so the potential is zero, the potential energy is zero, so it just has kinetic energy, then the Schrödinger equation reduces to IH bar multiplied by the partial derivative of the wave function psi with respect to time is equal to minus h bar squared divided by 2m times Laplacian of psi. And so this we can integrate and get psi at any time t, and so this allows us to determine at any time the quantum state of your particle. And I'm going to end my session here. So thank you very much, everyone, for listening, and I'm more than happy to take any questions.